So the goal of this talk is to discuss a certain kind of matrix factorization called the CUR matrix factorization. Let me first start off by introducing some notation by reviewing the singular value decomposition. So we're given an n by n matrix A, and we're given a rank parameter k, which is typically much less than the rank of A, which I'm denoting by rho. And we're interested in the optimization problem of finding a matrix X whose rank is at most k, such that the Frobenius norm of A minus X is as small as possible. And a solution to this optimization problem is given by the singular value decomposition, or SVD. So any matrix A can be expressed as the product of U sigma V transpose, where the columns of U are the left singular vectors of A. This is an m by rho matrix. The columns are orthonormal. We let U sub k be the top k left singular vectors. Then we have this matrix sigma, which is diagonal, and the entries are positive. Sigma 1 is the largest, and they're in non-increasing order. We let sigma k be the top k singular values. And finally, this matrix V transpose, the rows are the right singular vectors. And the top k, we let V sub k transpose be the top k right singular vectors, or equivalently the principal components. So a solution to this optimization problem is given by the Eckart-Young theorem, which says that X, the optimal X, is equal to A sub k, which is the product of U sub k, sigma k, and Vk transpose, or equivalently just projecting the rows of A onto the top k principal components. Okay, so this is the SVD. We're going to be interested in a different kind of matrix factorization, and we're going to be interested in a faster running time. So naively, the SVD would take mn times min mn time, whereas we're going to be interested in something much faster. Okay, so like I said, we're looking at the CUR matrix decomposition. So what is that? So it again tries to approximate A by a product of three matrices. This time, I'm going to call them C, U, and R. And the hope is that this product C, U, and R is such that the error term E has small norm. Now what is C? C is just a subset of columns of A. So it's not, unlike the SVD, it's not the top k left singular vectors. It's an actual subset of columns of A. R is an actual subset of rows of A. And U is some arbitrary small matrix which hopefully has small rank and hopefully makes this error term E small. Okay, so why do we care? What is some motivation for this? So here's an example where A is a user by movie matrix. The rows correspond to movies, the columns correspond to users, and maybe the entries correspond to likes or dislikes to those movies. And if we can get a CUR matrix factorization, then the factorization might be a lot more interpretable than the SVD. So for instance, if you're taking your top singular vectors, you might have some very strange linear combination of the underlying features. Whereas here you get an actual subset of users and an actual subset of movies. So in some sense, you can think of C as containing the most important users or the most important movies. Another benefit of this is sparsity. So in general, if your matrix A is sparse, there's no reason for singular vectors to be sparse. But here, if you're guaranteed that your columns and rows are sparse, then they'll still be sparse in this factored form. So that's some motivation. Let me formally define the optimization problem now. So we're given this matrix A, we're given a rank parameter k, and an approximation parameter epsilon. And the goal is to construct these three matrices, C, which is a subset of little c columns of A, R, which is a subset of little r rows of A, and U, which is a small C by R matrix. And what we would like is to achieve relative error, that the Frobenius norm of A minus CUR is at most 1 plus epsilon times the best possible for that rank parameter k achieved by the SVD. And so in general, it's not going to be possible to have C and R being k. They're going to have to be a little bit larger. But we would still like this rank of U to be very small. We would like it to be k. And, in this sense, we're getting sort of, we're comparing a rank k matrix CUR to a rank k matrix A sub k, as opposed to, say, a bicriteria solution. So we'd like to minimize these three parameters. Okay, so what is known about this problem? So here's a list of the most relevant prior work. So the first two rows, so these are works by Deterministic CUR and Mahoney. What they do, though, is they achieve additive error instead of the relative error framework that I described, which is sometimes okay, but in other cases, the error might be much larger if the singular values decay rapidly. They get roughly k over epsilon rows, k over epsilon squared columns. These are the type of numbers we're looking at. Then in work by Deterministic, Mahoney, and Muthukrishnan, they were the first to get relative error, 1 plus epsilon approximation, with k log k over epsilon squared columns, k log k over epsilon to the 4th rows, and a little bit higher rank, k log k over epsilon squared. The running time is also a little bit higher than earlier works, n cubed, as opposed to n in Z of A, which denotes the number of non-zero entries of your matrix A. So they were able to improve the number of rows to k log k over epsilon squared at the cost of a 2 plus epsilon instead of a 1 plus epsilon approximation. And finally, the state of the art prior to this work was a work of Wang and Zhang, which achieved k over epsilon columns, k over epsilon squared rows, and rank k over epsilon. And its running time is faster than the SVD, so n squared k over epsilon. So that's the state of the art, and there are a lot of open questions that remain given these works, and I've listed them here. So the first question is almost a purely combinatorial question, like what are the parameters of an optimal CUR? So how few columns and rows and small of a rank of matrix U can I choose and have a CUR factorization for any matrix A? The second question here is, can we design super fast algorithms for achieving these combinatorial parameters? Ideally, algorithms that run in the input sparsity of your number of non-zeros of your input matrix. And the third question is more about randomization. How crucial is that here? Can we get a deterministic algorithm for CUR decomposition in the same way that SVD is deterministic for the low rank approximation problem? Can we get a deterministic polynomial time algorithm? So those are the questions left open by these works. And so in our work, we resolve these questions. So the first question, the combinatorial question, is we give an algorithm which has to produce the optimal number of columns, the optimal number of rows, and the optimal rank of this matrix U, all up to a constant factor. So each is simultaneously optimal up to a constant factor. And moreover, we do this with a randomized algorithm which runs in time proportional to the number of non-zero entries of your input matrix A. So it achieves these combinatorial parameters with an optimal running time. Finally, we give a deterministic polynomial time CUR decomposition. It's actually slower than the SVD, but as far as we're aware, it's the first deterministic algorithm for this problem in polynomial time. So, okay, so before I state the results more quantitatively, I should also mention that we prove a lower bound which establishes sort of a benchmark of the parameters that we should be trying to achieve. I won't discuss it in the talk, the details, but what we show is that for any CUR factorization, so there is some hard instance. There is some matrix A for which if you want a relative error approximation, you need simultaneously at least k over epsilon columns, at least k over epsilon rows, and the rank of U should be at least k over 2. Okay, and this lower bound argument is similar to lower bounds in for the column subset selection problem, where you just care about finding a good C. You don't care about also finding a good subset of rows. So there's work on that by Deshpan Vempala, by Boutsidis, Drinius, and Magdan Ismail, Sinop, and Guruswamy. And we extend these lower bound arguments to this CUR setting. Okay, so these are the parameters we're trying to get close to. And our main theorem, our input sparsity time algorithm, gives a randomized algorithm achieving k over epsilon columns, k over epsilon rows, and the rank of u is k. And the guarantee is that with a constant probability of success, that the relative error, so you get a 1 plus epsilon approximation, and moreover the running time is number of non-zero entries of A times a log n factor, plus lower order terms, so m plus n times a low degree polynomial in log n, k, and 1 over epsilon. So that's the input sparsity time result. The deterministic algorithm also achieves the same, achieves the same combinatorial parameters, but its running time is a bit worse, so it's mn cubed k over epsilon. So we call the SVD, here would be mn squared, so this is sort of an additional factor of nk over epsilon. Okay, so those are the results, and I'm about halfway through the talk, and I only have a few remaining slides. They're kind of technical, but I'm going to go slowly through them. And the point of this part of the talk is to give you an outline of the algorithm. So it's sort of a skeleton structure of the algorithm where you can fill in various subroutines using either randomized algorithms or deterministic algorithms, depending if you're interested in running time or not using randomness, etc. So the first step of this algorithm is to find a good set of k over epsilon columns, this subset C of k over epsilon columns. And the very first step to do this is the following. We first compute an approximation to the top k right singular vectors of A, the top k principal components. So what I mean by approximation is we would like to choose a projection matrix Z1, Z1 transpose, so that so Z1 is an n by k matrix with orthonormal columns, so that when I project the rows of A onto this space, my error is, my cost is at most 1 plus epsilon times the optimal cost. Now, you know, if you were interested in a deterministic algorithm, you could just choose Z1 transpose to be the top k principal components. That's kind of slow. There's a lot of recent work on input sparsity time algorithms for low rank approximation, and you can get your space using those, your Z1, Z1 transpose using those algorithms. Okay, so that's the first step. You know, but we're not interested in in arbitrary linear combinations here. We're interested in rows and columns. So what are we going to do? So we're going to use leverage score sampling. So Z1 transpose is this k by n matrix. The rows are unit vectors. They're orthonormal. What can you say about the columns of this matrix? What can you say about the norms of the columns of this matrix? So these squared norms of the columns are called the leverage scores. And you can't say too much. I mean, you know the sum of the leverage scores equals k, because that's the sum of the row norms. You can show each leverage score is at most 1. Other than that, I don't know too much you can say. But what you can do is you can define a distribution for sampling columns from A proportional to the leverage score. So I'm going to sample the ith column of A proportional to the leverage score given to it by Z1 transpose. So what I'm going to do is I have this Z1 transpose, this k by n matrix. I'm going to choose order k log k columns from this matrix proportional to the leverage score distribution. And what I know is that, so those columns are, I choose indices, k log k indices between 1 and n. I choose the same set of columns from A. and I call that set of columns C1. And what I know from the theory of leverage score sampling is that if I project the columns of A onto the span of the columns in C1 sampled in this way, that I get a pretty good approximation to what I used to do the leverage score sampling. So the error I get by projecting the columns of A onto C1 is at most a constant factor larger than the error A minus the rows of A projected onto Z1 Z transpose. So we started off with a good space to project onto, which was some arbitrary space, and then we sampled from it and were able to get good columns to project onto, actual columns of A. So you can do that with k log k samples from this distribution. You can find this good subset of columns to project onto. But in fact, using a technique of Boutsidis, Frobenius, and Magnin Ismail, you can actually reduce this to order k samples. This is a nice adaptation of a Batsman-Spielman-Svirastava result for spectral sparsifiers. It's a nice application of that result in this context. And so the important thing to note is that by doing this process, I get order k columns in C1 which have this guarantee. But what we actually want here is we want the 1 plus epsilon approximation. And so this term here, A minus the projection of the rows of A onto the row span of Z1 transpose, is at most 1 plus epsilon times the opt, but we have a constant factor in front of that. So then another nice technique is to use an adaptive sampling trick of Deshpan and Vempala, which takes a constant factor approximation and drives it down to an epsilon approximation. So what it says is, suppose I've chosen order k columns, C1, and I have some constant factor approximation to the opt. I want a 1 plus epsilon approximation. So what do? I take all my columns in A, and I project them away from the columns in C, the span of the columns in C. So I look at the orthogonal complement to the column span of C. It's kind of like the residual, what's left after I projected away the stuff that's onto the column span of C. And so I get some residual vector. It has some norm. And I sample my remaining columns proportional to these residual norms, or the squared residual norms to be more precise. And a very nice theorem is that if I start with these columns in C1, if I additionally sample k over epsilon columns proportional to the residual norms, then I drive down the error here. So what that means is that, so this was a constant times the opt, and if I sample C2 columns, then the error goes down like k over C2. So if I set C2 to be k over epsilon, then this whole term here is epsilon times the optimum cost, Frobenius norm of A minus AK. And so overall, I get a 1 plus epsilon approximation inside the columns, the original order k columns adjoined with the additional k over epsilon columns I choose via adaptive sampling. And so that's what I'm denoting by this matrix C, the union of those two column sets. And moreover, a key property which we use in our work is the following, which is not only does this set of order k over epsilon columns of A give you a 1 plus epsilon approximation, but there's actually a rank k space sitting inside of this k over epsilon dimensional space, these k over epsilon columns. There's a rank k space inside of that which gives me a 1 plus epsilon approximation. So what that means symbolically is there's a matrix D which is rank k for which the norm of A minus C times D, so this is in the column space of C, is at most 1 plus epsilon times the opt. And we critically use that property. Okay, so at this point we've chosen k over epsilon columns of A. Now what do we have to do? So the next thing to do is to get k over epsilon rows of A. Okay, so the first thing to do is to use this observation I just mentioned about the columns that we've chosen. Namely, we know that there's some projection matrix, Z2, Z2 transpose, which projects onto a k-dimensional subspace of the columns we've chosen. So if I project the columns of A onto that k-dimensional space, I get a 1 plus epsilon approximation. That's what I've just argued, that there's some Z2 sitting inside of those columns. But, so how are you going to find this k-dimensional subspace? So if you didn't care about running time, and you just have n columns of A sitting in Rm, and you know there's some k over epsilon dimensional space which contains a good k-dimensional subspace for your problem, what's the best way to find that k-dimensional subspace? So the best way to do it is to take your n columns, project them all onto this k over epsilon dimensional subspace, and then find the best rank k approximation inside of there. And that's actually optimal by the Pythagorean theorem. But that's kind of slow. Like I got to project all my n columns onto this k over epsilon dimensional space in Rm. You know, how is that going to be input sparsity time? So what we do instead is we take these n columns and we take a small number of random linear combinations of them. And we instead project those onto this k over epsilon dimensional space in Rm. And that's much easier to do. Now they're all projected onto this k over epsilon dimensional space, and now we find the best rank k approximation to those projected points inside of that space. So, you know, we, instead of using all the points, we take random linear combinations of those points. And that's how we're able to find this Z2 efficiently. This good k-dimensional subspace inside of the columns that we've chosen. And now the rest of the argument is quite similar to what we did for finding the columns. Namely, so we have this Z2, which is this m by k matrix with orthonormal columns. What can you say about the row norms of this matrix? So these are the row leverage scores. And now if I sample, according to the leverage scores, if I sample rows of A based on this leverage score distribution, I can get k log k rows of A, which give me an error which is not much worse than the error I started off by using Z2 as my space to project onto. So it's a way of, here was a good column space, and I've translated it into a good row space to project onto by doing this leverage score sampling. And again, using BSS sampling, you can replace this k log k with order k. Okay, but now comes a sort of trick that I would like to call adaptive sampling plus plus. So this is a theorem in the Wang and Zhang work, which generalizes the adaptive sampling of Deshpande and Vempala. Basically what it says is, so Deshpande and Vempala intuitively says that, you know, I took my columns, I projected them onto some space, and now I looked at the residuals, and I sampled according to those residual norms, and I was able to reduce my error. I was able to reduce my error with respect to the best rank k approximation, A minus AK. That's what Deshpande and Vempala says. But what about some arbitrary k-dimensional subspace? Can I reduce my error with respect to that? And that's what the Wang and Zhang work does. So here what we're trying to do is we've chosen order k columns. Order k rows. We projected all of the rows of A onto these order k rows, and we looked at what's left, the residual. And we sampled additional rows according to that residual. And we drive down that error we want this to be epsilon. Now, to do that, first note that the space that we're comparing to, this Z2 transpose A, should have rank k. And that's precisely why we chose this k-dimensional subspace of the k over epsilon columns. If we were just to use the columns themselves here, this rank would be k over epsilon. And to drive it down this to epsilon, we'd have to choose k over epsilon squared rows, which is too many, right? We're trying to get k over epsilon columns and k over epsilon rows. And so that's why we did this additional work to find a good k-dimensional space inside of the columns. And so this adaptive sampling plus plus, what it says is basically, if I do this sampling of rows with respect to the residual norms, then I'm doing almost as well as this arbitrary k-dimensional space would for approximating A, instead of just A minus AK. So it's a little bit more general in that sense. And so basically, if I look at this term here, A minus the projection of the columns of A onto Z2, just by construction, this is 1 plus epsilon times the opt. This thing we've driven down to epsilon. This was already a constant factor times the opt. So the whole thing is a 1 plus epsilon times the opt. And if you look at this left-hand side, what is it? So we've projected the rows of A onto the row space. So R is the union of the two sets of rows we've chosen, one by the BSS sampling and one by the adaptive sampling. And this is actually your CUR decomposition, this term, because Z2 is inside of the column space C, this good set of K over epsilon columns. So Z2 can be written as C times some other matrix. So this whole matrix here is C times something times R, which is exactly what we wanted. So yeah, so I should note that computing this U, this matrix between C and R, can't easily be done in input sparsity time. So we have some additional ways of characterizing what that looks like in order to compute it quickly, or an approximation to it. So that's the outline of the algorithm, and let me just finish with sort of what tools we need to get the overall input sparsity time algorithm. So we use an input sparsity time low rank approximation and work with Clarkson, and I think Jelani might be talking about improvements to that in his talk. We use leverage score sampling of Jornius et al. We use this input sparsity time algorithm to find a good rank K matrix, rank K space inside of a larger space for approximating a set of points. This is work with Kanan and Vampala. The new tools we need here are input sparsity time version of the BSS sampling. We need an input sparsity time version of the adaptive sampling. And as I said, an input sparsity time construction of this little matrix U connecting C and R. For the deterministic algorithm, the main new tool we need is a de-randomization of the adaptive sampling of previous works. So basically, the other steps, the leverage score sampling, that can just be replaced directly with BSS sampling at a larger running time, but now it's deterministic. The adaptive sampling, we can show that these arguments in here only require pairwise independence. It's on a sort of continuous distribution, but we can discretize this distribution and have a small set of, a small probability space. So finally, just to conclude, we get the optimal combinatorial parameters for CUR in input sparsity time and also deterministically in a larger polynomial time. If you're interested, an extended abstract appeared in the last stock, and there's a fuller version on arXiv. So that's all. Thanks.